No discussion of egomaniacal behavior. I would never use that word. Anybody have any homework questions?
I need more help with principal stresses, but I'm
okay. Oh yeah, let's do it. Let's do it.
Okay. I'm still stuck on number 4 from last Friday's
okay.
assignment.
Principal stress. Number 4. Okay, so we have this stress tensor.
So yeah, I get to part C, and then I get confused about the corresponding coordinate system.
Okay.
And kind of what that means.
All right, so draw the stress element. What are the principal stresses? So we have to do those to get this. So I'm going to go eigenvalues of this matrix. We're going to go Q times that principal stress tensor times Q transpose 10, 0, 10, 0, 0, 0, 10, 0, 10. Okay, so the first thing to look for if you're sanity checking this is it needs to be symmetric. If this matrix isn't symmetric, something went wrong because all stress tensors are symmetric. And then the second thing is we know we should be able to, we know the absolute value, the biggest absolute value of shear stress in this new stress tensor needs to match this simple calculation that just says this. So we have this is equal to 20 minus 0 divided by 2, so 10 MPa. And so that makes perfect sense. Any questions about that?
What's the eigenvalue VC? I know that we didn't do that in this, but on one of the lecture videos.
Oh yeah, VC. So that's how you get the eigenvectors. This thing?
Yeah.
Yeah, so that'll give you, well, it's probably different for every calculator. On mine, that gives a matrix.
89, right?
Yeah, I have an 89. Is that what you have too?
Yeah.
Okay. So what that'll give is, like in this case, it gave 0.259.966. And then 0.966. Negative 0.259. And then the last one was 100. And so you know that they always are given in the same order as the eigenvalues. So this first column corresponds to the first eigenvalue it'll give you.
Oh, yeah.
Yep. And it's always, you have to always remember it can be plus or minus these. That doesn't matter. So if you're trying to make a coordinate system out of these, you just have to make x cross y equal to z.
Gotcha.
Yep.
That's the, I was going to ask, is that the, that's the stress tensor with the maximum shear stress, right? The result that we get.
This one after the 45-degree rotation, correct.
Yeah, okay,
Yep.
so make it-
There's not really much use for that. I mean, not in the way we're thinking about this stuff. Not if you're just trying to calculate like the likelihood of failure or something. That stress tensor isn't very useful, but
You would just do that simple
you would,
equation.
right, you would just calculate the max shear
What
stress
is it,
there.
max minus min over 2?
Right, yep.
So when you're showing us the eigenvector VC is just kind of a short way to find the vectors, but it's not really giving you the max shear.
The eigenvectors, eigenVC,
Yeah.
only gives you directions of the coordinate system
Okay.
that you're in. It just isn't very useful to us, but it's important to know that that information is available.
Could you distill out how you would have to rotate your coordinate system to get to that?
Yeah, for sure. Yep, exactly. And in fact, I didn't tell you this, but now I'm going to tell you. Like, people are always like, I'll bet there's an easier way to learn this stuff, and they just tell us the hard way. This is a case where that's true. But now I'm going to tell you. To express a vector, let's say, let me say it like this. To express an A coordinate system vector in coordinate system B, okay? The columns of the rotation matrix are the A coordinate axes expressed in the B coordinate system. In other words, so say that you're starting, so like for example, say that you're starting in this coordinate system, we'll say you're starting in your standard coordinate system. And you want a rotation matrix that'll express vectors and tensors in this new coordinate system that's like, sorry, that's a weird notation. So let me do it like, there's your X, there's your Y, and there's your Z that you're starting with.
But you like pull that out.
So this is the old X, Y, Z. Okay, and now let's say that we want to express that in a coordinate system. I'm just going to do one that I know is a coordinate system. So let's say 0.866, 0.50, negative 0.5, 0.866, 0, 0, 0, 1. That's your new coordinate system. Okay, so I didn't say anything about like what angle this is rotated about. I mean, you might be able to eyeball this and say that that's rotated 30 degrees about Z.
So wait, eigenvectors are the direction each principal axis is facing?
Correct.
In a rotated system? Oh, okay, well, yeah.
Yeah, exactly.
Okay.
Exactly. Right. Okay, so how do you come up with, I didn't say, I mean, imagine I, off the top of my head, could have come up with a more complicated looking coordinate system for the second one. It doesn't matter what it is. It could have all components everywhere. This one's just a simple rotation about Z of 30 degrees. But say it's a combination of 5 rotations superimposed on each other and you have no idea. Well, then what we have here is so I said that the rotation matrix columns need to be the coordinate axes of A expressed in B. Well, so this is the old one. This is our A coordinate system. This is our B coordinate system, okay? So let's do one where the axes are hold on. So let's do one where the columns are the B coordinate system expressed in the A coordinate system. Now notice that's the reverse of what we want, okay? But that's easy because we're just going from the identity to this one. So that's just 0.866, 0.50, negative 0.5, 0.866, 0, 0, 0, 1. Okay? And now, because the transpose of a rotation matrix is the inverse, the rotation matrix we want is just the transpose of this. So 0.866, negative 0.5, 0, 0.5, 0.866, 0, 0, 0, 1. And that's it. And we didn't have to know anything about what axis we were rotating around or anything. You can use that as a rotation matrix to re-express tensors and vectors.
So what if you wanted to find the angle?
Well, in this case, you could do it in 3 dimensions. Basically, angles are not usually the way to do things in 3 dimensions with some, counterexamples or whatever. But for the most part, it's pretty hard to tease angles out of 3-dimensional stuff.
Probably involves cross products or something.
I mean, you can use trig, because the 0.5, 0.866, that's
Yeah.
30 degrees.
So in this case, you can do it because we just did one rotation about z. But if we superimposed, first we did a rotation about z, then we did a new rotation about the new y, then a new rotation about the new x, it would be pretty hard to tease it out, Okay, so this isn't going to be useful in this class. In this class, we're just going to do rotations about x, y, and z. But it's probably a good thing to have in the back of your mind that this is all rotation matrices are. It's just coordinate axes of one coordinate system expressed in the other coordinate system. Any other questions about principal stress homework or anything like that? All right. So last time, what about the truss stuff? Everyone felt good on the truss stuff? Good enough? Nobody did it yet. That's what that means. Everyone's like, yeah, I haven't had any problems yet. I'm doing it tonight at 11. Okay, well, anyways, the truss stuff, remember why we brought up trusses? Because we're talking about uniaxial tension and compression. And trusses are a place where that occurs. Okay? There's another place where you only have tension and compression on members, and that is pressure vessels. And there are 2 kinds of pressure vessels we're going to talk about. So there are 2 cases. One is spherical. And so you have a hollow sphere, and you have pressure applied on the outside, I'll call that P sub 0 or P sub O, I guess. And then pressure on the inside, P sub I. And the other one we're going to do is cylindrical. And that is, I guess I'm going to leave the ends off. Like we don't know, just think of this as sort of continuing.
Infinitely long.
Yeah, really it just needs to be long enough that you don't have to worry about the weirdness that happens at the ends. And in this case, again, we have PO applied from the outside and P inner applied inside. And in both cases, we're making two assumptions. One is that the walls are thin. So let's say, so the thickness of the walls is much, much smaller than the radius. Okay. How much? It depends on your tolerance for imprecision, you know, but let's say factor of 10. Okay. And then the second thing is what we're going to call the pressure of the pressure vessel is the inner minus the outer pressure. So P is just P inner minus P outer. And for our calculations, the math doesn't do anything wrong if P outer is bigger than P inner, but the failure mode is different. It doesn't fail the same way. And so so you don't get good results the way we're thinking about it if P outer is bigger. What you get is buckling then, and we'll talk about column buckling at the end of this class. But for now, really everything we're thinking about is pretty much only useful if P inner is bigger. Okay, so let's calculate what's going on with these. And I think what's cool about both of these is that it's such simple thinking that leads you to the results here. And so remember how you derive these, because you can always, like I remember kind of the form of the formula. I don't remember the formulas themselves, which is which, but it's just so easy to remind yourself what the, so in both cases, what we're going to do is imagine slicing this thing in, you know, for a sphere, no matter how you slice it, we're going to do it in the middle. But any way you cut it into two equal sized hemispheres, you get the same answer. So, you know, we're going to slice it like that. For the cylindrical case, we're going to do one where we slice it in half like this. And we're going to do another one where we slice it in half like this. So for the spherical one, if you slice it in half and think of this as like a cut on an internal load. You know, we're not imagining physically cutting it in half. We're just like the half that we're isolating is, say, the bottom here. And what do you have going on? You have the adjacent material, metal or whatever, is applying tensile forces like this. And the pressure inside is applying a compressive force on the adjacent fluid. Okay. And if this thing is in equilibrium, those have to balance each other. So equilibrium means these total forces balance. Okay, so we have like a force F of the adjacent material pulling up here, and it's balancing a force F of the adjacent fluid pushing down. Okay, and we can calculate the, what's the force from the fluid? What's the pushing force that the fluid's applying? Well, that's equal to the pressure times the area. And since this area is a circle, this is just equal to P times pi times r squared. And now what about the force of the material? That is a tensile stress. And we're going to multiply that tensile stress times the area also. And the area for this thin wall is equal to the thickness times the circumference. So this is equal to the stress, that tensile stress, times 2 pi r times the thickness. And so that's 2 pi r t times that tensile stress. And now we can set these two equal to each other. So 2 pi r t tensile stress is equal to P times pi times r squared. The pi's cancel. One of these r's cancels. And you get that tensile stress is equal to the pressure times the radius over 2t.
This would be the gauge pressure.
Yeah, that's true. Yeah, right. And so what direction is this? If you think about how many axes of symmetry there are in the spherical case, like how many different ways we could slice this, what you get is that for a single point on this sphere, say that your coordinate system is like this. Where x and y, here, let me say it like this, the xy plane is tangent to the sphere. Yep.
Is the 2 pi r the inner radius or outer radius?
We're going to fudge that because we're assuming it's a small thickness compared to the radius.
But I suppose it'd really be like R2 minus R1.
Yeah, it would be like some kind of median. Yeah, that's true.
So why is it circumference and not surface area?
It is, well, it's the area of this ring. Okay, and so this is such a common, this is something you should get used to for derivations of anything where,
Oh, okay, it's
You
a
know-
derivation, so it's an infinitesimal portion of it?
well, that's how you usually use it. In this case, we're just saying it's thin, and so we're just gonna disconnect it and stretch it out into a long rectangle.
Oh, okay.
And the width of the rectangle, the length of the rectangle is 2 pi r, and the thickness is t. And just multiply them
It's just
together.
because it's negligible thickness?
Correct.
Okay.
Yes, the thicker it is, the more off that calculation is. That's why a lot of times you see it in, like you said, in infinitesimal, like integral type things. Bye, you too. Okay, so now what this says is if you have an xy plane that's tangent to the sphere at whatever point you're looking at, then sigma xx and sigma yy are both equal to PR over 2t, and sigma zz is equal to 0. Or in other words, the stress tensor is PR over 2t, 0, 0, 0 PR over 2t, 0, and then 0, 0, 0. Is it hard to find the principal stress tensor for this? No, that is it. Okay, so the topic that we're doing right now is cases where basically we have principal stress tensors that appear automatically in the way we do the calculations. Okay. Okay, let's just do a quick example with numbers. As you can imagine, it's pretty easy. You're just plugging numbers into this stuff. So let's say you have a spherical pressure vessel. And the radius is 0.1 meters. The thickness is 1 millimeter. The outer pressure is 1.01 times 10 to the 5 pascals. Why would I pick such a random number? Thermo people. That's standard atmospheric pressure. So the outer pressure is just standard atmospheric pressure. The inner pressure is 5.05 times 10 to the 5, so just 5 times atmospheric pressure. And we want to calculate the maximum shear stress for a point on this pressure vessel. Okay, well, the pressure, remember, is just the difference between these two. So 5.05 times 10 to the 5 minus 1.01 times 10 to the 5 is 4.04 times 10 to the 5. So the XX and the YY stress are equal to pressure, so 4.04 times 10 to the 5 times the radius, 0.1. divided by 2 times the thickness. And that is 2.02 times 10 to the 7 pascals. Okay, so what that says is our principal stress tensor is 2.02 times 10 to the 7, 2.02 times 10 to the 7, okay, so the maximum is 2.02 times 10 to the 7, the minimum is 0, and so the max shear is 2.02 times 10 to the 7 minus 0 divided by 2, and so the max shear stress is 1.01 times 10 to the 7 pascals. And then you can use that to calculate if you're afraid that pressure vessel is going to explode, you know. Here we're talking about explosion, like compressed gas or something, you know. It's more complicated to calculate. So, like, think about, you know, a submersible at the bottom of the ocean looking at the Titanic or whatever. It's a more complicated calculation to figure out what's going to happen there because it's not going to simply fail due to compressive stress. It's going to fail due to buckling, where you get a like a ripple in the shape and then it collapses at that ripple. And that happens way before you would see it collapse from just pure compression. You know what I mean? Like, things also could fail by pure compression, but they're going to fail way before that by buckling. Okay, any questions? Okay, that's all. Time for my meeting.